This is Sjostvan Nelson from Secura, and as part of the REWIRE project, we work on firmware analysis, which the demo will show you a little bit about. We want to perform firmware analysis within the REWIRE project because a lot of IoT devices are not designed initially with security in mind and only added as an afterthought. Neither is it easy to test any properties to verify whether it actually has been designed with security in mind properly. And especially if we want to test this at scale, this becomes very difficult because for a lot of devices, this would require actually purchasing a device before we're able to test this. So we want to use this with software to make this more scalable. We propose testing this with publicly available firmware images. And by publicly available, I mean firmware updates or full images that vendors provide on their websites. And for example, router firmware is usually available. Most vendors host this on their website, whereas firmware for OT devices is generally more difficult to acquire. I'm not talking here about source code, but the binary code within firmware images. And in the REWIRE project, we propose to analyze these by unpacking the firmware images and then selecting critical software components within these images and emulating these, after which we can test this emulation. As part of the REWIRE architecture, we're right in the middle here within the red square, where we have different components like the static analysis and dynamic analysis parts of our solution, which work together to offset the flaws and the strengths that they each have to optimize the discovery of vulnerabilities. The execution hook instrumentation is part of work package 4, which will be presented in a different slide deck. Our key contributions are the automatic vulnerability analysis for RISC-V based firmware. As part of this project, we contributed to open source projects to add RISC-V support to their analysis. Moreover, we only need binary codes from firmware images rather than source code. We add the ability to then analyze the firmware that only has binary code. Lastly, we provide control flow graph recovery of binary code, which later on allows us to perform attestation for the control flow integrity at runtime based on this control flow graph. So currently we unpack a firmware image belonging to the device that we acquired from the vendor itself. We identify a file system within this firmware, whereby we assume that it is using a file system as opposed to a monolithic firmware that consists only of binary code. Within this file system, we identify critical software components, such as cryptographic libraries or network services that are open to everyone with network access to the device. We emulate these pieces of software individually, which grants them still access to the file system in case they rely on other files, but doesn't grant them any interaction with other processes normally running on the device. And this saves a lot of computation power, which allows us to test it more quickly, with the trade-off that it can be less accurate when these processes do depend on each other. We automatically test these using binary analysis techniques such as fuzzing, whereby we generate inputs that make sense for this type of binary and run the binary with these inputs, and we observe its behavior. We report back when any faults are discovered in the software, which can be used by the security administrator to actually determine whether these constitute vulnerabilities and whether these are exploitable. Technically, the following flow is followed. So from the firmware, we extract things like custom code, network functionality, or cryptographic libraries. In the demo, we selected a Samba server from the ARM version of Router OS with an actual known CVE, so we can determine whether the analysis works as intended. The target is disassembled, resulting in assembly code. A fuzzing shield is generated for this target based on its behavior. A fuzzing shield, for those not familiar with fuzzing, is a process that wraps another process to make it easier for the fuzzer to supply input to this process, which can optimize a target by, for example, making it persistent. If you're testing a server, you don't want to restart this server for every input that it receives, etc. This is emulated using chilling, which uses the Unicorn emulator, which in turn uses QEMU. And the advantage of chilling is that it can also hook system calls using the Keystone assembler and provide other operating system abstractions. And the emulation is fast using AVL++. In the demo scenario, you'll see a firmware image being uploaded to a web page, which we create as a front end. This is a very basic front end. Any web page here could be used that connects to the later engines. There's a preliminary analysis stage, which gathers information that we can use in a later stage. Think about indicators for vulnerable functions, hard-coded passwords in the firmware. There's an entropy analysis, etc. These results can also be downloaded by the security administrator. The actual analysis is then started, from which logging output is also shown on the right. An example of results is shown, since actual analysis can take a very long time. And I'll then show a bit of a root cause analysis, which is from a pre-recorded video. So here I select the Router OS ARM version with a vulnerable version that we know to contain a CVE. Click Extract Firmware here, after which on the right you can see it has been extracted. The file system here is identified, which is squashfs. We then click Analyze. Since this is a fairly small firmware image, this takes not a lot of time at all. Depending on how large it is, this can take up to an hour or less. Here you can see there's also some preliminary results, functions, credentials, some custom binaries that it identified. In case we can actually emulate the firmware, we also scan the externally accessible network interfaces with Nmap, in which case these results are also added. In this case, it's not emulated because the emulation cannot gather the right properties automatically to do so. These results can be downloaded with download results, which we won't do at this time, part of the firmware. This also sends a message to the other engine, which does the actual fuzzing process. Which you can see here, just started the fuzzing. Since this can take a very long time to actually discover anything, we will not be showing this in the video, and rather show a bit of a root cause analysis that security administrator can perform with the results of this fuzzing test. With a pre-recorded video, where we have the CVE that I mentioned before. We can find this by looking for this version of the Router OS firmware on the National Vulnerability Database, where the CVE contains a very brief write-up that someone listed on GitHub, where we can see it's about the integer overflow on the Samba server of the firmware. So in this case, we actually knew that we needed for the demo to provide the Samba server to the fuzzing engine. So we have loaded the Samba server into the fuzzing engine, and here in a tool that we use to compare different versions. So we compare the patched version to the unpatched version, get an address which we can load into Ghidra, a reverse engineering framework, where we can find different functions that actually are very similar but not completely. And by looking at these functions in Ghidra, we can here, for example, find some things in the decompilation that can point us to the vulnerability. So we see here that there's some NTLM output, which suggests to us that this is in a pre-authentication flow of the server. We see our message anonymous user tried to log in, and since in the beginning on GitHub we saw that this was pre-authenticated, this to us points that this would be the function to look at and find the vulnerability, whereby security admin